Welcome, everybody. It's my pleasure today to introduce Keunsu Kim, and he will be telling us about exact multi-parameter persistent homology of time series data, fast and variable one-dimensional reduction of multi-parameter persistence theory.
Thank you for inviting me. My name is Keunsu Kim. I'm a PhD candidate at PostTech in the Republic of Korea. I will talk about EMPH, exact multi-parameter persistent homology theory for time series data. I collaborated with my advisor, Professor Jae Jung, and I assume the audience have a basic understanding of a TDA concept. I will proceed my presentation as the following order. First, I review the sliding window embedding. And second, uh, I will explain the background of sliding window embedding and introduce a new concept, Liouville torus of time series data. And third, briefly review multi-parameter persistence theory. And fourth, our main proposed theory of exact multi-parameter persistent homology, briefly called EMPH. And we applied our theory to toy example. Sliding window embedding is a well-known method in TDA for time series data. Sliding window embedding translates time series data into point cloud. So it enables us to apply vectorless Lisp filtration to the point cloud, which result in we get the persistence barcode. Here, M is the embedding dimension parameter, and tau is the delayed parameter. In this talk, we set tau equal to pi m plus 1 because to translate the sinusoid functions into circle. So we set tau equal to pi over m plus 1. If not, then sinusoid function goes to ellipse generally. By the definition of sliding window embedding, we easily check sliding window embedding translates sinusoidal functions into a circle, and trigonometric polynomial goes to closed curve in n torus. Here, n is the degree of a trigonometric polynomial, and it is important to choose sufficient high embedding dimension to preserve the geometric information. For example, if we set m equal 1, then sinusoidal functions goes to line segment. On the other hand, if we choose m larger than 1, then sinusoidal function goes to circle. So to preserve the geometric information, the choosing sufficiently high embedding dimension is important. And Gawker and Fourier proved twice degree of a trigonometric polynomial is a sufficient embedding dimension. And now I introduce the Liouville torus and the background of a sliding window embedding. Actually, I realized that I had an error in my paper a few months ago. My friend called me around midnight, and he said he found an error. So I tried to correct the error and stayed up all night, but I failed. So I canceled every schedule and correcting the error, spending 2 weeks. To correct the error, I introduced the new concept, Liouville torus of time series data, and the new archival version is uploaded. And my experience in symplectic geometry was helpful to correction. My mistake was, for example, A is subset of R2. Then I use this equation. But this is not generally called because in the figure, the equality is not ordered. So I had a foolish mistake. So I correct the new version from this duration for this duration. Before introducing the Liouville torus, it is important to understand the meaning of sliding window embedding for time series data. The motivation, we can derive the motivation from Takens embedding theorem. The following schematic illustration summarize the Takens embedding theorem. Given dynamical system, M and pi, this is called the dynamical system. M is called page space or state space. Is the collection of all possible state. And the pi represents the trajectory of particles. We want to analyze the dynamical system M and pi, but we do not have a knowledge. We only have sampling measurement. We measure at x, then we get the real number yx, and we measure at pi x, then we get the real number y pi x. So our sampling measurement represented by time series data. Takens embedding theorem tell us that from this time series data, we can reconstruct manifold which is diffeomorphic to M. Therefore, we can infer or analyze the topology of this dynamical system. And this is familiar for many people. Sliding window embedding for discrete time series data, or is called time delayed embedding. Assume that our discrete time series data comes from dynamical system. Then Gn is represented by Gn equal y over pi to the n x. Here n is the initial point. Then by the Takens embedding map and the Zero's sliding window embedding, Zero's slide window, for example, given time series data, and consider the sliding window from this duration goes to 1 point. This is Zero's point. And the move slide window, move sliding window, and translate another point. This is a first point. In the case sliding window goes to case point. So sliding window embedding method in time series data analyze the shape of trajectory on M. Now, let's define Liouville torus of time series data. Given time series data F, we define Liouville torus denoted by psi F. Here, R LF is twice modulus of L's pre-coefficient. By definition, sliding window embedding is encompassed within the Liouville torus. In this figure, sliding window embedding, for example, cosine 3t goes to red curve by sliding window embedding. And the green one is Liouville torus of this time series data. Actually, Liouville torus is an object in Hamiltonian dynamical system. So before, so in this example, two uncoupled one-dimensional harmonic oscillator. For example, picture is there is a spring M1 and there is a independent spring. Uncoupled means they are independent. Then each Hamiltonian described by like this. And each trajectory of a particle governed by Hamilton's equation. For example, in this case, Pi equal Qi equal round H round Pi dot. Yes, governed by Hamilton equation, and the particle's state is determined by its momentum, its position and the momentum. So each page space is R4, and each trajectory is in this page space. The trajectory that conserves the energy of each harmonic oscillators, then it should be located on the two torus. This is the example of Liouville-Arnold theorem, and this two torus is called Liouville torus in this Hamiltonian dynamical system. If omega 1, the ratio of omega 1 and omega 2 is a rational number, then trajectory is a closed curve on the two torus. This corresponds to periodic time series data. Otherwise, trajectory fills the two torus. This corresponds to quasi-periodic time series data. In this talk, we only focus on periodic time series data. Now we connect two concepts, the Liouville torus of a time series data and the Liouville torus of a Hamiltonian system. We proved sliding window embedding of a time series data can be formulated by the trajectory of an uncoupled one-dimensional harmonic oscillator. More precisely, we proved sliding window embedding image is isometric, metric to trajectory. But we use Vietoris-Lipsch complex. So in the barcode sense, we have the same barcode. This is the meaning of can be formulated by the trajectory of uncoupled one-dimensional harmonic oscillator. And this table shows us the relationship between sliding window embedding and uncoupled one-dimensional harmonic oscillator. Here, n is the trigonometric polynomial degree, is corresponding to the number of harmonic oscillators, each with a frequency multiple of the fundamental frequency. So this is the number of n is number of harmonic oscillators. And the delayed parameters corresponds to the mass of each harmonic oscillator. And this is RLF is twice of modulus of L's coefficient corresponds to energy of each harmonic oscillator. And the sliding window embedding is encompassed within Liouville torus. We obtain the Liouville torus of time series data can be formulated by the Liouville torus of uncoupled one-dimensional harmonic oscillator. In short, analysis of sliding window embedding corresponds to analysis of shape of trajectory and two different time series data on the same Liouville torus as identical when their conserved quantities are equal, even if their initial conditions or shape are different. This implies that analysis of the Liouville torus is closer than the sliding window embedding. But I do not intend closer is closer to negative meaning. When comparing two objects A and B, it is important to consider the perspective. Two objects may appear same from one perspective, but they appear different from another perspective. So the difference between sliding window embedding and the Liouville torus is just a different point of view. And the Liouville torus have much more symmetry than the sliding window embedding. It enables us to find the exact formula of the persistence barcode. That is the reason why we analyzed the Liouville torus rather than sliding window embedding. So I want to emphasize on there is no need to exclusively rely on sliding window embedding. And the Liouville-Arnold theorem tells us that we can use the same logic to another integrable Hamiltonian system. Integrable Hamiltonian system means integrable is a Hamiltonian system have a sufficient, have a maximum invariance. By symplectic structure, the Hamiltonian system have at most n independent conservatives. Let conservatives denoted by C, and the level set is LC. The trajectory in the LC means the particle moves, particle's trajectory preserves the quantity C. And Liouville-Arnold theorem tells us that LC is dpomorphic to N torus. So the fourth example is our previous slide. One-dimensional, uncoupled, one-dimensional harmonic oscillator is integrable Hamiltonian system. So I will introduce the multi-parameter persistent theory briefly. Multi-parameter persistence theory was introduced to address shortcoming of a single parameter persistence theory. For example, single parameter persistent homology is vulnerable to outlier. It has a stability theorem, but small perturbation. It is a stable under small perturbation, but it is vulnerable to outlier. And when we want to use multiple filtration simultaneously, we should introduce multi-parameter persistent filtration and homology. But the challenge in the multi-parameter persistence theory is there is no description of a complete invariant. Complete invariant means that if two objects have the same complete invariant, then they are isomorphic. Complete invariant is a representation of a persistence homology. For example, in the single parameter persistent homology or model, barcode is a complete invariant. So alternatively, we consider incomplete but practical invariant favored barcode. In the multi-parameter space, we reduce the multi-parameter filtration onto this ray. Then this filtration becomes a one-parameter filtration. Therefore, we can define barcode on this ray. This is a favored barcode. And now our proposed theory of EMPH. This is a strategy of our EMPH theory. Adams, Jack, and Adams proved the barcode formula of Vietoris-Leibs complex of a unit circle. And Gaucker and Perea proves persistent Queen's formula. Persistent Queen's formula is useful when we calculate the persistent barcode of a product space, when we know the barcode of each component space. And we generalize the persistent Queen's formula to apply Liouville torus. And the Liouville torus is the product space of circles. Therefore, we can deduce barcode formula of Vietoris-Leibs complex of Liouville torus, and we generalize the result from single parameter to multi-parameter case. That is EMPH theory. Recall the pipeline of TDA. Given point cloud, we apply Vietoris-Leibs complex. Then we get the collection of simplicial complexes, and we assign each simplicial complex to a point in a parameter space. And then applying homology functor, we get the barcode. This is a pipeline of TDA. And I will explain this procedure. Adams, Jack, and Adams proved barcode formula of a circle under Leibs filtration. And result is this formula. And Gaucker and Perea proves general persistent Queen's formula, and we generalize the condition from finite metric space to totally bounded metric space, because circle is not finite metric space but totally bounded metric space. So to apply persistent Queen's formula to circle, we should generalize the condition. Note that in the persistent Queen's formula, the product space equates with maximum metric. So from these two lemmas, we get the barcode formula, n-dimensional barcode formula of Liouville torus under Leibs filtration. So this formula reveals the relationship between TDA of the Liouville torus and Fourier analysis, because this term is the object in TDA, and the LF is twice of modulus of L's Fourier coefficient. This is an object in Fourier analysis. And we generalize the from single parameter to multi-parameter. We construct a multi-parameter filtration and homology. For example, given time series data, each Liouville torus is two torus because this time series data consists of two Fourier mode. This is two torus. And the two torus consist of two circles. First circle's radius is 1. This radius is 1. And the second radius is 1/2. And we apply Vietoris Leaves complex to each circle. This means that we apply Vietoris Leaves complex to each circle and then producting them. And we assign product simplicial complexes, this simplicial complex to a point in multi-parameter space. Then this is a multi-parameter persistent homology. And then we consider one parameter reduction of a multi-parameter filtration. We get on this layer. Then this filtration becomes one parameter filtration. We can define barcode in this way. So this barcode is denoted by like this. And we proved a barcode formula of a circle and the persistent Queen's formula on this layer. Where is Finally, we get the fundamental theorem of EMPH theory. From this formula, so in the multi-parameter space and ray L, and the direction vector is A, and the end point is P. So barcode formula on this way, formula is like this. From this formula, single parameter persistent homology is a special case of EMPH, selecting just the diagonal ray. Diagonal ray means A equal 1, 1, and B is 0. Then in this case, this term is 1, and the PL is 0. This is 1, and this is 0. Then single parameter persistence formula. From our fundamental theorem, we can establish the relationship between TDA and Fourier analysis through EMPH theorem. For example, selecting direction vector corresponds to weight of each Fourier mode. And selecting endpoint corresponds to threshold of modulus of Fourier mode. And k-dimensional barcode corresponds to select top k Fourier modes and choose the smallest. Select k Fourier mode and choose the smallest among them. Actually, I think it is similar to k parameter in persistent landscape. So we can develop the methodology of Fourier analysis within the framework of TDA and vice versa. Now I will show you the simple calculation given time series data. This is a single parameter case. The barcode, one-dimensional barcode of a Liouville torus is given by this. And in the multi-parametric filtration, we select the diagonal ray. Then each barcode is given by this. So this example confirm the single parameter persistent homology is a special case of selecting diagonal ray. So this is a claim. And if we choose another ray in multi-parameter filtration, then we get the different barcode. That is important. Selecting a different ray in multi-parameter filtration, that gives us variable point of view. And we also propose the curved filtration like this. This line piecewise linear curve. In this case, in the barcode sense, cosine t equal cosine 2t. Cosine t and cosine 2t. They are same. Their barcode is same. And cosine 2t is different to cosine. Sorry. No. Cosine t is different. Cosine 2t. No, 2 cosine t is different to 2 cosine 2t. And they are different. So I summarized our research is a famous saying from Henri Poincaré. Mathematics is the art of giving the same name to different things. Because in the previous example, curved filtration, cosine t equal cosine 2t, 2t, and the different cosine, 2 cosine t, different 2 cosine 2t, and different. But if we select diagonal ray, then we can easily check cosine t in the barcode sense. This is barcode sense. Cosine t equal cosine 2t, and 2 cosine t equal 2 cosine 2t, and they are different. And if we choose another ray like this, then cosine 2t, cosine t is different to cosine 2t, and different to 2 cosine t, and different to cosine 2t, and then different. So selecting array in multi-parameter filtration, that gave us variable topological point of view. And we also proposed collection of arrays. There is no reason we consider only one ray. We can also consider the collection of arrays. We define the barcode on the multiple of arrays like this, and we also proposed given ray split L into L1 and L2, because we want to give a different threshold to each parameter. Recall that endpoint corresponds to the threshold of modulus of parameter. So we want to more general setting. We also propose the splitting. So I apply our theory to toy example. This is a four-shape data comes from Kegel. Our theory is for time series data. So we should pre-process the image data into time series data. For example, using Python library, selecting a point in boundary 1, 2, 3, 4, and measure the distance between center and these points. This represented by time series data. Note that the fluctuation is lower than other shape because the circle's radius is constant. So fluctuation is small compared to other classes. And we apply k-means clustering. The left thing is we choose a diagonal ray in multi-parameter space, and we choose another ray given by direction vector is this, and the end point is like this. And in this case, when we choose a diagonal ray, star splits into two subclasses. And the other thing is typical, it's a result what we expected. So EMPH provided variable topological inference. And we plotted the subclass of stars. The left thing comes from cluster 2. And the middle thing comes from cluster 3. And latter thing is pre-processed time series data comes from cluster 2. And blue thing comes from 3. So selecting diagonal ray distinguish this subtle difference, and choosing another ray disregard this subtle difference. And we also applied our theory to supervised problem, three-class classification. This data consists of 3 classes, and compared to other traditional method in TDA, persistent homology of sliding window embedding with infinite norm. And the sliding window embedding with the Betty sequence and persistent image and sliding window embedding and the Vietoris Leaves complex equate with 2 norm and the Betty sequence persistent image. And our method is after EMPH, and the vectorization method is Betty and the persistent image. Then we get the comparable result to the traditional method. Our method classification accuracy is this, and usual traditional method is very similar, comparable. And this is a computation time. This red arrow is our method. Our method's computational complexity is highly low because we used precomputed barcode formula, so we can save much time compared to other traditional method. So summary of our research is we introduced the Liouville torus and its background, and EMPH is a topological data analysis on the Liouville torus of time series data. And EMPH reveals the relationship between TDA of the Liouville torus and Fourier analysis. And EMPH provides the variable topological inference, for example, for shape data. And the computational complexity is highly low, and we get comparable accuracy performance to the single parameter persistent homology method. And I want to persistent keenness formula for p-norm. Fourier and Gackel proved persistent keenness formula product space equal to with maximum metric. And if someone proved the persistence keenness formula for p-norm, we can obtain EMPH for p-norm. So we get the various inference method for time series data. So I wanted someone prove keenness formula for p-norm. So please visit my homepage, and thank you for your attention.
All right, before we get to questions, why don't we briefly unmute ourselves and applaud for the speaker. So questions for Keunsu? Yes, Nicholas, please go ahead.
Yes, thanks. Thanks for the lovely talk. I was wondering if you have compared your method, in particular this last experiment that we showed, with some traditional spectral methods.
Yes.
Like non-TDA methods.
This slide?
Yes, exactly.
So what's your question?
Well, you could, well, the most naive thing would be, I don't know, regard the spectrogram, you know, as a vector and feed it into some machine learning. Or you could do some, like, I don't know, but, you know, signal processing is a serious subject, and people have spent a lot of time doing this kind of time series classification based on a spectrogram. And I was wondering how your method compares to that work.
I did not check because in TDA network, many papers comparing in TDA method. So I did not check the not TDA method.
Okay, but I think it would be very interesting. Thank you.
Further questions? Keunsu, there was one thing that I didn't understand. I'll have to check out your paper maybe, but you know, I understand the computation of these barcodes of the torus. But then how does your data feed into that? So how does the data?
Because where is the definition? This is a definition. RLF is twice of modulus of L-Fourier coefficient. So given time series data, we apply fast Fourier transform. Then we get the yes, we calculate the RLF. So we can calculate the Liouville torus.
I see. So from your time series data, you compute these Fourier coefficients, and that gives you the radii of the different dimensions of your torus.
Yes.
And then another comparison would be, what if you did the clustering or machine learning on that sequence of Fourier coefficients? I guess that's going along the lines of Nicholas's question. Instead of turning it into barcodes, treating it as a vector of Fourier coefficients.
Yes. But I did not check, but because when I read many papers in TDA, they are just comparing in TDA method. So I did not check yet.
Gotcha. Further questions? Yes, Nicholas.
If I may have another one. So how do you choose your threshold of truncation up to which degree you compute the Fourier transform in practice?
Actually, in this paper, I randomly choose. I randomly just like a hyperparameter. We choose using our experience, and my ongoing research is how to select the frequency or ray in multi-parameter persistent filtration. So ongoing research is how to select frequency and the ray automatically. So this is ongoing research.
Thank you.
I just had a comment. So you asked this question about Kunith for the LP metric. I just want to mention one paper by Gunnar Carlson and Benjamin Filipenko, where they look at the L1 version of this. So I put the link in the chat, but it's called persistent homology of the sum metric. So the L1 version. Now they study this, but it's more complicated than the L infinity version. So with the L infinity version, you have a complete description up above. With the L1 version down below, it's been studied, but there's no complete answer yet.
I will check it.
Yeah. All right. Any last questions, at least for the recorded portion? Well, if not, thanks so much, and let me end the recording here.